All right, so this equation, there's a lot that goes into this equation. You can almost really split it up into three parts. Really, the left-hand side, the middle, and the right. The right-hand side, that is the effect of doing work. You get kinetic energy change. In order to actually transfer any energy through work, that's primarily mechanical energy change, right? You'll have a kinetic energy change. The middle part, the integral, okay, what it's saying is that if you have a net force on an object, the object will displace. But just because you apply a force on an object doesn't mean that it'll actually move in the direction that you apply your force, right? We've said this time and time again, is that forces create accelerations. They don't necessarily relate directly to velocities, right? Velocities where you're actually going, accelerations where you're going to be going. So you can apply a force on an object without causing it to displace in the direction of your force, like circular motion. When you look at uniform circular motion, the acceleration is towards the center, but your tangential velocity is always perpendicular to your acceleration. So when you look at uniform circular motion, and you have your tension in, and then you have your tangential velocity like this, and they're perpendicular. Your tension doesn't do any work, because if it's uniform circular motion, the velocity of your object shouldn't change. And if your velocity is not changing, your kinetic energy is not changing. If your kinetic energy is not changing, that means there's no energy transferring in or out. So all that's happening is this changing direction. And so that's why it's important to note the dot product. When you apply a force on an object, it needs to also, your force that actually causes it to move in a certain direction is what's actually doing work on that object. Okay, so and again, as it moves, it may change its velocities or whatever, but
so there is no work
in this case, in uniform circular motion, there's no work done. It has to push along V. Okay, it has to. At least not has to, but it's only the component that is in the direction of V that does work. And then you add it all up. And when you add it all up, you get this number or this value that we measure in joules that we call work. Now, the reason why I want to split the left side as work is that there are many different ways you can do work. And when you add work up, you can kind of look at the work contributed by individual forces or individual pieces. So you can kind of piece work together. You can be like the work done by friction and the work done by someone pushing on it and the work done by gravity, and you can add it all up. And when you do that, you'll find that certain kinds of forces do work in a certain way and certain kinds of forces do work in a different way. And eventually we'll find that there's conservative forces that do conservative work and non-conservative forces that do non-conservative work, and that's where we end up splitting this up. So they all have kind of different conceptual meanings. This is like the net effect, this is how you quantify it, and this is kind of how you use it in combination of other things. Yeah?
Is there an equation where we can equate force to energy?
Well, it just depends on the force and it depends on the energy you're trying to represent. So that's actually what we're going to try and do today is look at a couple specific scenarios or specific forces and look at how their energy is quantified. Let's see. Okay, so first things first, let's look at gravity. Okay, so the easiest scenario to look at for gravity is free fall. Okay, so we look at free fall. Essentially, you have an object that is falling. So I know I talk about potatoes a lot, but I actually literally have a potato here. So if you have a potato and it is falling, okay, we're only looking at the scenario where it is falling. Okay, potato of mass m, it falls due to gravity, force of gravity. Is a baked potato, is quite warm. They're warm. Yeah. Okay, and then what we're going to say is we're going to say positive y is up. Okay, so we sum our forces in the y direction. You know, applying our Newton's second law, we get that the only force is negative mg. Mg coming from the force of gravity, that's essentially the weight. It's negative because it's downward when we count positive y is up. And that is equal to m dv dt. Okay, so I'm not saying ma, I'm saying dv dt because, again, we're going to use the same chain rule trick that we did last time on this. It's just that last time when we used the chain rule trick, we looked at a general force, right? This time we're looking at a very specific force so that we can actually come up with a specific expression. So the chain rule trick was, instead of looking how velocity changes with time, we want to look at how velocity changes with position, based on where it's at, not how much time has passed by. So negative mg equals to m dv dx, or sorry, I'm going to say dy, because I'm going up and down, times dy dt, that's the chain rule part, right? V to y as y to t. And that gives, this part here is essentially the velocity. So this gives mv dv dy. Okay, so here's the left side, here's the right hand side. I'm going to move this dy over. I get negative mg dy equals to mv dv. Okay, before I move on, I want to make sure that you guys understand physically what these expressions are saying. There's a, if math is the language of physics, you gotta be able to understand what it's saying. So mg, that's the weight. We're looking at the contribution of the weight over a infinitesimally small displacement, the dy. That is what dy means. Whenever you have the differential amount of whatever, dy, dx, dv, dt, you're looking at a very, very small slice. The limit at which that slice goes to 0, that makes it an instantaneous moment, an instantaneous separation, an instantaneous velocity change. Dt would be an instantaneous moment in time. That's what we're trying to get at when we use the dv dt, whatever stuff. Okay, so how weight is connected with an instantaneous change in distance, and how your momentum is related to an instantaneous change in velocity. Okay, so ultimately what this equation is saying is, how does changes in position relate to changes in velocity? They are scaled by the mg and the mv. Okay, so from here, now we'll do the integral. We'll integrate both sides. Okay. And again, what does it mean now to integrate each side? If mg dy is looking at the weight applied over a small distance, the integral is to add it up over a macroscopic distance, a full amount of position change, right? So not instantaneously, but add up all those little instantaneous moments and find out what the net effect is. That's what integrals essentially help us do. They determine the net effect. Okay. So another way to look at it is if you look at the equation or the graph. Okay. If I were to graph this, I'm trying to take slices in terms of y, and this is generally true whenever you take integrals. Whatever it is that you're taking the differential slices of, that's kind of the function that you're interested in, right? You're interested in the variable y and how mg depends on y. How does mg depend on y? It doesn't. So it's constant. It's flat. And so when you look at a differential slice, you're looking at this area, right? So you think of this as like the height of your rectangle, mg, and then the width of your rectangle is the dy. That's what mg dy represents. The integral of mg dy represents from a certain spot all the way from an initial y to a final y. That's what the integral means, is to add up a bunch of these little slices. To add them all up. Okay. So until you take that integral, you're only looking. This is looking at one individual slice. This is looking at all the slices put together. So in the same way, you can draw a graph that represents this one. Okay. So for this integral, you have v, right? Because your slices are in v, and you're comparing it to mv. Now, what does this graph look like? It's linear, right? So it'll be like. And now we're looking at, again, if you're looking at mv dv, you're looking at an infinitesimally small slice. And this is where it gets kind of tricky when you start learning about Riemann sums. You talk about right-hand Riemann sums, left or right side, left side, or center Riemann sums. As you get small enough, the idea here is that the thickness of dv is so small that it is effectively just at, representing that particular moment on that graph. So you're not worried. Yeah. And so then this is that mv at that particular moment. So what calculus lets us do is it lets us add up all the area under this. From here to, it not necessarily have to go all the way to the left-hand side. I mean, it could stop like right here. Some initial velocity, some final velocity, right? And so the integral represents all of that space, adding up them all. Okay?
Wouldn't it be intersected at zero?
Yeah, I guess so. I guess this should go through 0, but yeah, that makes sense. Because you're not adding any constant here. Okay, so in any case, this is what they represent. This is what they mean. You're adding up all that stuff. At least as far as the technique goes, how to actually calculate any of this, I told you guys it's kind of like looking for the antiderivative. Okay, you're looking for the derivative of what expression gives you mv. Okay, and that would be 1/2 mv squared. Right? If you take the derivative of this expression with respect to v, you'll get this expression. When you take the integral, it's not just taking the antiderivative, though. You're looking at a range of this, from the left side to the right-hand side. So you're taking it from the initial velocity to the final velocity. Okay. Again, I'll leave it to your calc teacher to prove to you why this mathematically works. I'm just telling you technically what you do. Like I said, when you teach like first graders and kindergartners how to add, and you tell them to put two numbers on top of each other and carry the one, you don't explain to them why that works. You just tell them that's what you do. You just do it. You do it. You just do it, and then later, once that becomes, yeah, then it makes it a lot easier to explain to them why that works. Although I think Common Core is trying to flip that around, but whatever. So that's the right-hand side. So the right-hand side is this, and then we call this kinetic energy. And then we said this is essentially a change in kinetic energy. Right? So this is the right-hand side, and the right-hand side is really not any different from the notes that you should have taken last time. What I want to show you is what happens with the left-hand side. How do we calculate the left-hand side? These are constants. When you have constants, or I guess another way to put it is the derivative of what expression gives you mg with respect to, when you take a derivative with respect to y. So the derivative with respect to y of what expression equals to mg? It'd be mgy. So you have negative mgy from y initial to y final equals to delta k. So this expression here, we're going to call this U subscript G, which is our gravitational potential energy. Okay. Now mgy by itself we'll call gravitational potential energy, but this together is actually saying a negative change in UG. I should specify UG is going to be mgy without the negative. Okay, without the negative. UG is just mgy. That is the potential. You'll find is often used to represent potential energy. So that is the potential gravitational potential energy. You're looking for the change in it, and you're looking for the negative change in it. Gives the change in kinetic energy. Okay, so let's back up for a second, make sure we understand just all this number or this math that we've just done. We said that if you add up the effect of the weight over all these distances, because it's such a simple function, it turns out just to be linear. The higher something is, the more potential energy it has, gravitational potential energy it has. The lower it is, the less gravitational potential energy it has, and it's linear. It's linear. So if you were to graph UG versus Y, it'd be like this. Right? What we're saying is then that as you gain gravitational potential energy, you must lose kinetic energy in this scenario. In this situation, if you're only talking about free fall objects, if I take a pen and I throw it up, right? I start with the most kinetic energy when it leaves my hand, and that kinetic energy transforms into gravitational potential energy as it reaches its maximum height. At its maximum height, it no longer has kinetic energy, and it's all gravitational potential energy. Then that gravitational potential energy transforms back into kinetic energy as it falls. I lose gravitational potential energy, and I gain kinetic energy. So when this delta UG is negative, the negative of that makes it a positive delta K.
Just in general, delta U equals to delta K.
No. The negative of delta U is equal to delta K. The negative is important because that means that when you lose potential energy, you gain kinetic energy. When you gain kinetic gravitational potential energy, you lose kinetic energy. They have this opposite relationship. Okay? A couple other interesting things to point out about this. Again, this is specifically for a free-falling object. So if you take the potato and the Earth and you consider them as one system, okay, so you have the kinetic energy of the Earth and the potato, and you have the gravitational potential energy of the two together. If your potato is the primary thing that's moving, right, then you should have a conservation of energy there. Your energy should be conserved. In other words, this transforms 1 to 1. Or alternatively, the change in K plus the change in UG should equal to 0. If you put them together, right, there should be no net change after you put everything together. Alternatively, you can also write it like this. The initial potential energy plus the initial kinetic energy must equal to the final potential energy plus the final kinetic energy. Right? These two statements are mathematically equivalent. They're saying the same thing. You can't have a change in the energy of your system. Okay. Questions? So I want to, now this is all kind of that middle part. I want you guys to think about the work done, the way work is done. Whenever work is done on a system, okay, positive work done to a system should increase its kinetic energy. it gains energy. Negative work done to a system should slow it down. It should take energy out of the system. So I want you to look at how gravity is doing work on the potato. If the potato is falling downward, okay, then gravity is in the direction of the motion. Your gravity is doing positive work on the potato if it's falling. As it's falling, what happens to the potential energy? Potential energy is decreasing. So a positive work leads to a negative change in gravitational potential energy. Oops. Positive work done by gravity leads to a negative change in gravitational potential energy. When you go in the other direction, if the potato was thrown upward, if the potato is moving up and gravity is still down, they are in opposite directions. The gravity is doing negative work. So it does negative work on the systems, taking energy out, but as it goes up, it's gaining potential energy. So that negative work done is transforming the kinetic energy into gravitational potential energy. Same thing. Negative work leads to positive gravitational potential energy change. Positive work leads to negative gravitational potential energy change, right? Okay. So what's the point? Why do we care about all this positional change stuff? Why can't we just use everything that we've already done? Well, consider for a minute that I have a ball on a swing, and it swings downward here, right? And it starts out at rest, and then it ends up going this way with some velocity, and I want to know how fast it's going. Okay, I want to know how fast it's going. It can be kind of tricky. See, everything we've done up until now, we can tell how fast it's going only when it's at the very bottom. At the very bottom, gravity is in the opposite direction of the tension, and I think even then, it's really hard to determine how fast it's actually going, because you don't know what the acceleration is, which means you don't know how offset the tension is from the gravity. There's all sorts of things going on here that it makes it actually very difficult to use Newton's second law to determine how the motion of this behavior, of this ball, just going on a swing, right? Gravity is this way, tension is this way. Your tension is always radial, but gravity is not always radial. Some of it is radial, some of it is tangential, and as it swings, it's changing all the time. The amount of gravity that's tangential and the amount of gravity that's radial is changing all the time. Which means that if you try and do Newton's second law and you sum your forces are not constant. They're changing. Which means that your acceleration is changing. Which means that, there's all this stuff that makes this very complicated to try and solve if you try and use Newton's laws. Instead, if we just say that it started at a certain height and ends at a different height, we know it starts with a certain amount of gravitational potential energy and it ends with a certain amount of kinetic energy, and we can actually figure out the net effect of gravity pulling downward on it every step of the way. The integral already takes care of that for us. What the integral told us is that it doesn't matter how it moves sideways. All that matters is that it changed vertical positions. Changes in vertical positions necessarily result in changes in kinetic energy. So you can say that mgy initial plus 1/2 mv squared initial. Sorry, I'm writing this kind of weird. Must equal to mgy final plus 1/2 mv final squared. Right? This is basically saying that, which means that this is just mgh. One thing I forgot to point out, when you look at this equation for gravitational potential energy, y, the value of y is relative. You have to have some zero, right? So maybe if you're in this room and you're doing an experiment and you're dropping something on the floor, you probably use the floor as 0. But if you're flying an airplane over the Pacific Ocean or something like that, sea level might be 0, and so on and so forth. So what you consider 0 gravitational potential energy is all relative. Same thing with kinetic energy, same thing with momentum, right? It's all relative to how fast things are moving. Gravity is based relative to how high something is. So in this case, I'm going to say that at the bottom of the swing, that's 0. But it doesn't really have to be at the bottom swing. The powerful thing about this is I can figure out how fast it's going partway through the swing too. All I need to know is how far it has swung or how high it is. So if it starts out without any kinetic energy, then this will be 0. And if it has fallen to a certain distance, and I make that my reference level, that can be 0. And then that will tell me how much velocity it has. Avery, what's up?
Is there like a purple notebook spelling of it? Thank you.
So then that's pretty much what we have. All we needed. We know that my gravitational potential energy leads to this kinetic energy. And if I solve for my velocity, I get this. Which is actually a very interesting result, because maybe this looks familiar to you. Yeah.
So, I've got a question on the velocity. Would be velocity in the y direction, or velocity in the x direction? Because y as our
It's true. It is the actual velocity, the magnitude of the velocity. So it doesn't have to be in the x, it doesn't have to be in the y. It is the net velocity. Yeah. It's true. We did all of this in the y direction, but this is where I was saying, sometimes you look at the math and you gotta try and reason it through with the kind of the conceptual side of it. If we really look at gravitational potential energy as an energy, and that energy is conserved, this must turn into kinetic energy. Kinetic energy, you don't have kinetic energy in the x, you don't have kinetic energy in the y. Kinetic energy is just, your velocity, your magnitude of your velocity, which is important. Kinetic energy is not a vector, so you can't split it up into x and y. Momentum is a vector, you can split that up into x and y. Kinetic energy, you cannot. So whenever you deal with kinetic energy, it has to be the actual magnitude of the velocity. That you can figure out the kinetic energy of your object. Okay. Let's see. So, energy is conserved in a scalar fashion. So you can't just say, well, some of your energy is in the x direction, some of your energy is in the y direction. It doesn't work that way. Especially because I think the biggest giveaway is it's squared. Whenever you square something, you can't really the vector method stuff doesn't really work out well. So anyway, good question though. This is the actual velocity. So if I didn't look at it when it's at the bottom, if I looked at the velocity of the ball as it was swinging halfway through, it would be its velocity at the angle, in that angle moment. Okay. All right. Now this 2gh. This is a very interesting conclusion. Does anyone recognize this particular expression, square root of 2gh? We've actually seen it quite a bit. Michael, you remember? Yeah.
wasn't that on
VT
the very
squared
first
over.
batch? Like the third thing. Wasn't that something like that?
Not,
That was a step in it.
no, that was different. That's like a. It's like a.
It was a step in it. I remember.
This has shown up. Okay, so I'll give you the scenario where this shows up. When you have free fall, if you do kinematics on a free fall, and you do the v squared final minus v initial squared equals to 2g delta y. And you say that, okay, so it falls, and also your initial velocity is 0 if it's dropped from rest. You end up getting this. So I think it's really interesting because how can an object that is falling freely end up with the same velocity as an object that is swung sideways, going over the same amount of height change? Yes, it's the same work put into the system. The only thing that is actually doing any work here and here is gravity. Now, if you look at it and say, but Mr. Mack, how about the tension? Well, that's interesting. Why would tension not do any work in this scenario? Akash.
It's not like acting in any direction, like it's not retaining any of the energy because this is just energy of motion in this plane. Because it just forces it. It doesn't cause any acceleration on the object.
Yeah, it is. It's accelerating it. It is accelerating it, but yeah.
It's not pulling the object up.
It is holding the object up, it's accelerating it, it's turning it, it's applying a force, it's there, but
There's no net change in velocity because
there's no net change in velocity. That's not technically correct. Its velocity is changing because it's changing direction. The tension is changing its velocity,
magnitude of velocity.
but not the magnitude of velocity. Your tension is not acting in the direction of your velocity. Your velocity is always perpendicular to your tension. It's like uniform circular motion. Your tension is not actually causing it to change position. Your tension is not causing it to go towards the string or away from the string. The radius of the string stays the same, right? Which means that your tension doesn't actually apply a force in the direction of movement. And so therefore it does not actually do any work. Okay, it's not, the tension's not doing any work, but your gravity is. Your gravity is pulling in such a way that there's a component in line with its velocity. And so it speeds up and then it slows down, right? So your gravity is causing it to speed up or slow down. Your tension is not causing it to speed up or slow down. The tension is only causing it to turn. So that means that your tension's not doing any work, gravity's the only thing doing work, and so when you look at it from the perspective of energy, it is the only thing doing work, is the only thing putting energy in or out. And so you get the same result. That's really powerful, because what it's saying is that for certain kinds of forces, especially a force like this that is only dependent on its position, its vertical position, it tells you that the way something behaves does not influence how its energy changes or the outcome, right? It doesn't matter if this goes like this or if it is going down a slippy slide. It doesn't matter if it's, you know, like if you go to a doctor's office and they have those little ring things for little kids.
Yeah.
It's the same. It's the same energy change. Except in those cases, you know, you probably have significant friction, so you have energy loss. But if there's no other actual forces doing work, it doesn't matter how it falls. As long as it falls a certain height distance, it will gain the same amount of kinetic energy. Its velocity will be the same. Okay, so that's why we're analyzing and studying energy. Is because there's a lot of situations like this where it's very useful. Roller coasters, for example. You know, when you look at roller coasters, how do they know that you're going to make it when you go into that vertical loop? How do they know that you have enough energy at the beginning to make it all the way through? Well, you know, they do the calculations, right? Okay. Any questions about gravitational potential energy? This is how you calculate it. This is how you calculate it near the surface of the Earth. Okay, so keep that in mind. We assumed M and G are constant. Turns out G, as you get really far away, you know, changes. So we'll have to adjust for that later. All right. The other force that I want to investigate is the spring or elastic force. Okay. So you look at the spring or elastic force. We haven't really talked about how to model the spring or elastic force, so we're going to do that now. We're going to, let's say, for example, you have a spring attached to a block, and that the surface that it is on is frictionless. Okay, so this is going to be a new kind of force. Just like we had, we went through all the different kinds of forces, normal force, friction force, so on and so forth. We never really talked about a spring or elastic force yet. This is how we're going to model it. I really do say specifically model it because not all things behave this way. If I take the, if I take the wooden meter stick, wherever my meter stick usually is. Yeah, I showed you. You know, you bend it and it comes back. That's elastic. Things that have elastic behavior are things that kind of have a restorative force that bring it back to its original shape. Not all elastic things behave according to this model, but a lot of things do.
There's points when every single elastic phase does not behave.
Yeah, there's no way. So first, let's define an equilibrium position. Okay, so generally speaking, when you look at something elastic, it has some sort of resting shape or position. If we stretch it out, okay, we pull it out, then we'll see that for a certain position S, there will be a restoring force F sub S to represent the force from the spring, and it'll be back towards the equilibrium position. For this purposes of this, our calculations will say positive X is to the right. And so to also kind of help with our calculations, S and S sub E being the equilibrium length. This is representing the spring. You know, you look at a spring; it has volume, right? It takes up a certain amount of space, and then it's attached to something. And sometimes it's useful to use the length or distance from the wall or where it's attached, because sometimes you compress it. So if you compress it, you need to be able to go in and out. But I will use the equilibrium position as the 0 for X. Okay, so if S represents the distance from where it's attached, X represents the distance from the equilibrium position, the equilibrium line. So X will be S minus SE. It's kind of nice. It's you don't always, you can do everything in terms of S, but it just becomes cumbersome. It's nice to do it in terms of X because we're going to see it just wiggles around X. So we call this, or we call an ideal spring as one that follows Hooke's law. And I'll show you Hooke's law in a minute. Okay. Hooke's law says that a spring has a restorative force that is directly proportional to how much it's stretched. So if you look at my spring scale, right? If I stretch it, you know, it's all evenly spaced. Isn't it strangely convenient that my spring has a stiffness so that if I stretch it this far, it's 5 newtons, and I stretch it exactly the same distance, it's another 5 newtons? That's what is meant by a proportionally restorative force. It's directly proportional, and so we say it follows Hooke's law, or you can say it's Hookean. It's a Hookean spring. So I stretch it this far, it goes to 10. I stretch it this far, it goes to 15, right? I don't know, it's not exactly a centimeter, but, you know, I will call it a centimeter for the sake of simplicity, but for every centimeter, it's an extra 5 newtons of force that's resisting me with, right? So since it is linear, if we were to plot the stretch versus the force of the spring, we're saying it's linear. It's linear. Not only that, but I guess technically it's linear and it's restorative, which means it's actually like a negative F. It's backwards. So if X is positive, this should be negative. So you can write it like this, or I guess you could draw it the other way where it's like, you know, sloping down. But either way, it's linear, and so there's a slope on this. And the slope of that we call K. And the K is called the spring constant. Kind of like how there's a coefficient of friction, which is a number that is a measure of the stickiness of surfaces. The spring constant is a measure of the stiffness of your spring. The higher this number, the stiffer your spring is. The more force it takes, to have any change in x. Okay, so you can write it like this, or you can write it like this, or you can write it like this. They're all saying the same thing. They're all saying the same thing. They're saying that you have to stretch your spring in order to have it apply a force. Okay, so here's the thing. As I take my spring scale and I pull it down, right, I'm clearly putting energy into it because I apply a force in one direction and it's applying a force in the opposite direction. It's doing negative work. It is taking, I'm applying, I do work this way, it does work the opposite direction, and so that when I get to this point, the plastic still has no kinetic energy. It's not moving, right? So there's energy stored here, so that when I let go, it flings back, right? There's kinetic energy stored in the spring. Or, sorry, not kinetic energy. There's energy stored in the spring that comes back. That's kinetic. So the question is, how do we quantify this energy? If I stretch it, this 3 centimeters or whatever, or if, it's reading at 15 newtons or whatever, how do I know how much energy is here so that when I let go, I can figure out how many joules of kinetic energy comes back and so on and so forth? Well, we can follow the same approach that we did for gravity here. I can sum my forces in the x, and if it has displaced a certain amount and I let it go so that the spring's the only thing applying a force on it, I'll have this. This is my force acting on it. And that will lead to some change in velocity, right? So this force is quite clearly a function of position, which means that it makes me think it acts like a potential energy. It acts kind of like gravity to a certain degree. We can talk about the work done by it. We can relate the work done to position, so on and so forth. So here's what I want you to do. I want you to try and analyze similar to how we analyzed gravity. Okay. See how when we analyzed gravity and we did this dv dy thing and we moved it over, we came up with this expression for gravitational potential energy? I want you to determine if there is a spring potential energy and if that's related to the change in kinetic energy in some way. Okay. So if you're not sure where to start with the chain. Okay. Start with that. Okay, start with that. Think about how we did gravitational potential energy to see if you can determine if there is a spring potential energy. You got 10 minutes. Give it a shot. How's that? Oh. Oh, yeah. That is. Yeah, you can give it a shot.
Wait, what happened?
The metal was reflecting light into his eyes.
Oh, yeah, so.
You know what? Let's just use tape.
Didn't see any.
You could use your aluminum foil from your potatoes.
That's
But
also
then my
reflective.
potatoes will be exposed.
Oh, but the aluminum foil is also reflective.
Yeah,
That's smart.
I'm trying to keep it much. I designed it so that.
Uh-oh. What's going on?
Because the tape would be shiny as well.
R in terms of R, right? We are solving.
It's fine. If they haven't complained about it, there's a shiny in your eyes still.
Yeah.
Really? That part too?
So we're trying to solve for delta U. We're trying to solve for delta U. What is delta U? Delta U is when mass velocity squared over 2 is equal to 1 v.
Didn't really want to.
Yeah, actually, it is. Right?
Is it just
Is it 1/2 kx squared?
the negative?
Cool. So I've got one thing. We have. So is it force equal to delta x though, or is s equal to x? Or x equal to s? Okay, yeah, there we go. Never mind. I was getting a little confused there. Sorry about that. Equal to x, then everything works. Yeah. Exactly. Okay, so. So, so delta k is equal to so delta k is equal to 1/2 negative Spring actually that's
They would not cancel because I tried that, but if you cancel them out, they wouldn't solve it. Well, actually,
So now I've got one question. Are you thinking that delta k is equal to negative 1/2 k? Are you, so is your delta k negative or not? Yeah, it's delta k, kinetic energy is negative 1/2. Negative 1/2 k, which is constant, x squared. That's what I got. Okay, sweet.
so that means that the change in potential
It's equal to, it's not, no, it's equal to u. Yeah. The negative is equal to x. Yeah. Negative. Oh, so then yes. Well, depends on, yeah, right? Because if x is positive in this direction. X equals r on I feel like that's the way to do it.
You can't find out.
Well, let him tell us if we have a negative sign.
So this is yes, so in the end it would be positive. Because delta k is negative.
No, as x increases, your energy. Take energy in the negative direction.
Potential energy builds up. Yes, we know that the change in k is
Yeah,
negative.
yeah. So as x increases, you have
So from this point to that, so after you release it, there's less it's more kinetic energy, but it's going in a negative. Yes. So yes, so the spring potential is positive. The change in spring potential is positive because you go from having but
What's the case name?
So from here it has no kinetic, but it's in the negative.
Oh, yeah.
So that's it. Really high, and then
I can like 160, and I'm like I've got like 45. I got 45. I just hit like have like a white towel underneath the laptop, and then I just come back on the
kinetic to be positive. That's what is we calculated but negative kx
I went like 160, but I don't have and not to mention you need like your freaking like 3,000 internet encryptions worth of
because these are since yes, so since base negative. So stretching it out, increases the it decreases the yes, and then because it eventually stops, so that means there's no more phase again. So this is potential, then you release it, magnetic, it doesn't stop. If it stops, it doesn't have it has a lot of That was unclear. I imagine you can't get to going because it's so the book doesn't really explain how to find the sound object and the problem is expected. You expect that to more than
What is this?
Yeah, if it's divergent, it's great. Showing up and sending numbers is 0.
Oh my god.
Yeah, that's what I was saying. So you convert it to the it's like the geometric sequence. But if you can, that's the tiny part. And then the last part of the homework it's like it's easier if it's kind of done. Yeah, it's like express this number as and it's like 2.417 and it's kind of powerful because you can actually find that exact number using the sequence.
All right, guys. We gotta move on because we spent some class time on a story. So let's go through this derivation. So start with the chain rule. Negative kx equals to m dv dx dx dt. Okay, the dx dt is essentially your velocity. So you have negative kx equals to mv dv dx. Okay, move the dx over. Negative kx dx equals to mv dv. You're going to integrate both sides. Okay. Notice the similarity in the structure. You have a constant times a variable, and you're integrating with respect to that variable. You have a constant and a variable, and you're integrating with respect to that variable. So if this one became the change in 1/2 mv squared, then this one is going to be the negative of the change of 1/2 kx squared. Okay, now I'm taking a couple shortcuts here. I'm not really writing it out in the most explicit format, but if you use the parallel from here to here, you can kind of see how I'm getting this. So I'm going to, if this one we call kinetic energy, I'm going to call this one the spring potential energy or elastic potential energy. Now this is the elastic potential energy for an ideal spring or ideal elastic material, which means that the object that you're stretching has to behave like this. It has to be something with a linear restorative force. Okay, so then we can say negative delta US equals to delta K. And that is, interestingly, very similar to what we had before. Or whoops, this is period 5. Where was our... See, we had something very similar with gravity. negative delta UG equal to delta K. Now we have negative delta US equals to delta K, which means that the behavior is similar. When you lose spring potential energy, you gain kinetic energy. When you gain spring potential energy, you must lose kinetic energy. So when you take a spring, a spring, like a nice spring, a spring that can compress and expand. Actually, I think that might. Do we have one more really nice? All right, we'll just use a slinky. I'm gonna use a slinky. And I'm gonna use weight. Okay. So when you look at something that now this doesn't behave totally Hookean, but maybe. The way it behaves, this oscillatory effect, right? If I let it come to an equilibrium, okay, there's a certain stretch, there's a certain gravitational potential energy on this, but more importantly, if you look at the elastic potential energy, if I now stretch it beyond, right, it wants to keep oscillating through the equilibrium position. The equilibrium position is where it should be the fastest, right? Because that's where you have the least amount of stretch, which means you should have the least amount of elastic potential energy. And so that's when you should have the fastest movement, is through the equilibrium position. And then when it gets to the other ends, where it's stretched or compressed the most, that's when you should have the most elastic potential energy, and therefore the least kinetic energy, so it comes to a stop at the ends. Ah, yes. So that's a pretty good one, too. Right. So, start with equilibrium, and then when you stretch it beyond, right, you're looking at where is it the fastest. The fastest is in the center, where you have no elastic potential energy. So what you're seeing here is this jumping between these two. Kinetic to potential, kinetic, potential, back and forth, back and forth, back and forth. It has the most potential at the ends, where it's stretched the most, and that's pretty much it. Okay? So, we can say the same thing. Whenever it is stretched out, as it is going out, as it is going in the positive x direction, the force is in the negative x direction, it does negative work. As it is stretching out, your spring is doing negative work, but you're gaining elastic potential energy. So the work done by the spring will always be correlated with a negative potential energy. As the spring does work on your object, it's losing potential energy. As the spring does negative work on your object, you're gaining potential energy. Okay? Okay. So if you compare these two, between gravity and the spring, you'll see that we keep coming across this US, this potential energy U. Morgan. Okay, so we can kind of generalize this in that some forces you can conveniently do this kind of analysis. Not all forces end up having such a simply integrable force, right? This force was purely a function of position. This force was just constant. And so it turns out that, or rather, this force didn't depend on position. Some forces are conservative this way. So let's look at conservative forces. In general, conservative forces are only functions of position. Okay. One thing to note about gravity, gravity is not exactly a function of position. It's constant, but it is always facing in the same direction everywhere you go. It doesn't depend on anything else. A non-conservative force like friction, although you can have constant friction, friction can change directions, and it's dependent on a variety of things. It's not constant, right? And so friction is not a conservative force. One other thing that is not important to note about conservative forces is really primarily that the work that a conservative force does, it can always kind of get it back. There's this kind of switching back and forth between your force putting work into the system and doing work, negative work, pulling energy out of the system. It has this back and forth. Non-conservative forces can't really do that. Friction only usually takes energy out. It doesn't ever really put energy back into a system, right? It just dissipates kinetic energy and turns it into thermal energy. It doesn't really give back this mechanical energy. So when we look at gravity and we look at the spring force and we look at how we can define a gravitational potential energy or a spring potential energy, all conservative forces have some sort of potential energy function. When I say a potential energy function, I mean something like this exists. There's no expression for friction. There is no U for friction. It doesn't exist. Because friction is not conservative. You can talk about the work done by friction. You can talk about how friction can change your kinetic energy. But you can't really do this chain rule DVDX kind of analysis on friction. It doesn't work. Because friction is dependent on a lot of things outside of just position. If you're talking about an applied force, if you just go and push on something, right? That's not a conservative force usually. So it doesn't have a potential energy function. There are a lot of forces that have potential energy functions, but there are a limited number, and that's what we study. There's specific ones, we figure them out, and then we can apply them. Generally speaking, for any conservative force, you can say delta U is negative W, or the other way around, W equals to negative delta U, whatever. There's this opposite behavior between the work of that force and the potential energy from that force. Yeah, sorry. So if you have, again, with gravity, as you lift something up, it does negative work. And so then you gain potential energy. As the object is falling, it's doing positive work, but you're losing potential energy. All conservative forces have this kind of dichotomy, this opposite behavior between the work that it's doing and the potential energy that it has. So in general, for conservative forces, there is such a thing as a potential energy function, and the negative change of that potential energy is equal to the work done by it, which is determined by that dot product. Okay, so this is, for all forces, you can do this. For conservative forces, you can define this. Only for conservative. Yeah. All forces have this. You can define work done by all forces. But only conservative forces have potential energy. And then if you have the net force, then you can relate it to the kinetic energy change. That's why in all our examples, we only singled out that particular force. Once you start adding a bunch of other forces in there, you got to take them all into account before you can actually look at the kinetic energy change. Okay, that is it for part 2.